Alright, so we had another circuit. We got through with our first three base equations for all the different loops, and we started combining them together. So we've got loop 1 and loop 2 combined together, equation 1 and equation 3 combined together to give us two brand new ones. And this is where we left off. So now what we need to do is we need to take these two equations and we need to keep working them down to solve for one of the variables. So we have 59K IB minus 9K IC is equal to 25. There. The second equation we have is negative 9K IB plus 36.5K IC is equal to 100. So now we want to take this guy, we want to set them equal to each other. And this one, we don't have a great option, so we're just going to brute force them. So we're going to multiply our top equation by 9. We're going to multiply our bottom equation by 59. And so that gives us 531K IB minus 81K IC, and that is equal to 225 for the first equation. Second equation, we're going to get the negative 531K IB plus 2.1535 meg IC is equal to 5,900. We're going to combine these together by adding them. IB will fall out, and we're left with 2.0725 meg IC is equal to 6125. Stay. We divide both sides by the 2.0725 meg. And our IC current comes out to be 2.955 milliamps. You good there, Morgan?
No.
What'd you get for your IC?
I got 924 million. But I did equation 1 and 2 and 2 and 3.
1 and 2 and 2 and 3 versus?
Yeah. Is there like, shouldn't that work out?
Should work out the same way.
What happened?
We just did on the same problem, and I found that I actually added some factors instead of multiplying them to each other. So
Okay.
that's what I had is wrong.
Okay. So you did which equations, Morgan?
1 and 2 and 2 and 3.
Okay. Let's go ahead and work through those. So we've got one value for IC. Let's continue on with where you did. So you said 1 and 2 and 2 and 3. Did you have the same equations though? For 1, 2, and 3?
Yeah.
Okay. Let's do this. Let's bring this guy down. And we'll slide him over. Come on. Oh, for the love of Pete. I'm so confused. Where did all my notes go? So 1 and 2. So equation 2, we had negative 1K IA plus 12K IB minus 1K IC. That's equal to 0. That one's equal to 25. Good there? Which value did you go through and get rid of? Okay, so to get rid of your IAs. So we got our 5K IA plus 60K IB minus 5K IC still equal to 0. Those are going to drop off. We good there? Okay, so we'll label this as our number 4. And then you said you did 2 and 3. Is that what most people did, was 1 and 2 and 2 and 3? Okay. So 2, we start off with minus 1K IA plus 12K IB minus 1K IC is equal to 0. And then equation 3 is minus 4K IA minus 1K IB plus 10.5K IC. And then we got to get rid of the A again. So we multiply top guy by negative 4. So that gives us 4K IA minus, 48, not 36. 48K IB plus 4K IC equals 0. So this equation's now been changed. We combine them together, IAs fall off. We end up with a negative 49K IB plus 14.5K IC equals 0. Okay. Gotcha. Are we still good, Morgan?
Yeah.
Okay. So this is going to give us equation 5. Now we're going to jump back up here and grab our 2 equations. We're going to combine them together. So we got the 59K IB minus 9K IC equals 25. And the minus 49K IB plus 14.5K IC equals 0. Okay, how do we go from here? Okay, and which one did you get rid of? IB. Did you use 49K or 59K? Okay. So we have 59,000 times 49. It's going to give us 2.891 meg minus 9,000 times 49, 441K IC, and 25 times 49 1,225. We good there? Now we're going to multiply the bottom, so we end up with a negative 2.891 meg IB plus 14,500 times 59, 855.5K IC equals 0. Combine these guys together. 855.5 minus 441 gives us 414.5 K. IC is equal to 1225. There it is. Divide both sides by 144.5 K. Those dang negatives. They always get in the way. I'm not going to lie, I was starting to get a little worried and questioning myself. Not going to lie. Because we're coming through as we're doing this, I'm like, okay, everything is matching up so far. I'm just like, oh please, make sure I didn't screw it up when I was typing this out. Yeah. Like I said, it's nothing against you. It was just more of a, oh crap, I hope I didn't make a mistake in my math. Which we've proven happens from time to time. It wasn't even about that. It was just, I hope I don't prove myself an idiot. So, the good thing is we did it two separate ways. We got the exact same answer. So we're doing it, I'm doing it correctly. That's the biggest thing. Okay, so now that we have that, now we can work backwards. And again, it doesn't matter where we go. I'm going to move back to the way I was solving it just because I have my notes on hand. So after we get to this point, now we're going to go back one step. So we're going to take our IC, we're going to plug it into one of the equations that we used at this step, so either 4 or 5 because that's all we have, and we're going to solve down for IB. So we're going to take 59K IB minus 9K times IC, which is 2.955 milli, equal to 25. This is 59K IB minus 26.595 volts. So just remember, as we're going back and forth, what units we're in is equal to 25. We add the 26.595 to get it across the equals. And we have 59K IB is equal to 51.595. Divide both sides by 59K. And again, we've got volts divided by resistance will give us current. IB comes out to be 874.492 microamps. Very good there, except for Morgan. And Jameson, I guess.
I messed up on that before. Still going strong somehow.
Still going strong. Okay, so now that we have IB and IC, now we can go back to one of our original questions. Do you have a question, Spencer? Okay, gotcha. I thought I saw a hand, so. Okay, so now we go back, and again, we put it into one of our original 3 equations to solve for IA. So we have 5K IA minus 1K times our IB current, which was 874.492 micro, minus the 4K times our IC, which was 2.955 milli, equals 25. And so what we get here is 5K times IA minus 874.492 milli minus 11.82 equal to 25. We add these two guys together because they're going to both be negative, and then we get that total value. We're going to add that to both sides. So what we end up with is 5K times our IA current is equal to 37.694 volts divided by 5K. IA comes out to be 7.539 milliamps. We still doing good? We still got people hanging in there? Any questions about that? We're matching up for those that are left? Do what? Somewhat. Again, it just comes into how you do your rounding. And here's where Zach loses it. You're welcome. Okay, now we got to figure out what currents we have where. So the biggest thing is these are the guys that we're looking for, but we have to find the different voltages across all of them. So we have, just so we can go back and double check everything. But the biggest things we're looking for is the current we have through R3, the voltage of R3, the power of R3. Then we have the current of R5 and the voltage of R5. So primarily looking for this one and this one. So to solve for R3, we have the two different currents. So we got 7.539 milliamps for current A. For current C, we have the 2.955 milliamps. And current B was 874 microamps. The reason I'm dropping off the decimals on the microamps is because at that point we're talking nanoamps compared to milliamps. We don't care. That is so far out of our accuracy at this point, that's not going to make that huge of a difference. Yeah. We're two steps smaller. Okay. So when we have here, we're going to look at R3. So we've got 874 microamps of current coming this direction. We've got 2.95 milliamps of current going this direction. Which one's going to win? IC or IB? IC. So our current going through this guy is going to be going in this direction, giving us a positive to negative polarity. We're going to subtract the currents because they're opposing each other. And so what we end up with across R3 so we got 2.081 milliamps. Did you get them all right? Okay, what's the voltage across that resistor? 2.081 volts. Okay, what's the power across R3? Now we go to R5. We have current from A coming down. We have current for C going up. Which one's going to win out? Current A. So we're going to have current going this direction, giving us positive to negative polarity. And what's the value of that current? 4.584 milliamps. And our voltage?
I'm within it.
You're within 5%, so that's good.
We're at 4.9.
Almost threw him off the wagon there. Almost. Okay, so we end up with that. But then the last thing we want to do is, so that's all that the question would be asking for. But for my own sanity, to make sure I got the right answers before I would submit it, I would do a couple of double checks to make sure that my values are correct. So what I would need to do is I would go through and I would solve for the voltages across R1, R2, and R4 as well, just so I'd have the values. So what this comes out to be is we have 6.665 milliamps with 6.665 volts. R2, we end up with 8.74 volts with the 874 microamps. R4, we have the 2.95 milliamps, and that gives us 16.253 volts. Now in this, to double check, I'm going to go through a series of loops to make sure we get back to our original voltage. So no matter which path we go, they should always add back up to this voltage. So the first one we go through, I'm going to start with on the green arrow. I'm going to come up and around and just go around the outside. So all we're going through is R2 and R4. So we know we have 25 here. We should have 25 positive that direction because we have 25 negative. So we get 8.74 in the 16.253, 24.993 volts. Okay, so we're good that direction. The other way is we want to do this loop between R1 and R5. So again, we have the 6.665 and we have the 18.336. That gives us, we go this loop is 25.001 volts. So again, roughly the 25. And the last check is we want to incorporate one loop that goes through R3. So this one, I'm going to go down R1, across R3, and down R4. So we get the 6.665 plus our 2.081 plus the 16.253. And again, that gives us 24.999 volts. So just as a sanity check, I always like to go through and make sure that any direction I go is going to add up back to the 25. Because it can be really easy, because there's a lot of information we have going on in here that we're kind of cramming into a small space. We can drop a digit, we can move the decimal point, we can even change our positive or negative values. Yeah, there's a little bit more to keep track of, but you can just lay it out from top to bottom, and you're not gonna stop here and then go back to this point and then redo everything here, type of a thing. So yeah, I agree with that. There's less moving parts, and this is more of a logical flow through things. Okay, any questions about mesh? What's that?
So all those that have the double supply,
Mm-hmm.
and it's positive on the top, always, right?
Mm-mm. That can switch.
Okay. So how do you deal with those switches of the batteries when you switch them?
All it's in your equations right here.
So that's just the negative 25 would be positive and negative depending on.
Yeah. So if this power supply here was flipped, this value would be a positive 25, and then when we would solve it all down, all of our currents would essentially be negative because we're measuring from top to bottom. Because when we make these loops, we're assuming conventional current flow, going from in clockwise from the positive to the negative.
So you would assume counterclockwise in those cases?
You could, yeah.
Okay.
But I would just, and anything that we do, I would assume that we're going clockwise. So here's an answer to your question with this guy. So with our equation, it's going to fall into loop B. So here we would have the R2 times IB minus the R2 times IA. So we cover this guy. Then we get to this one, which is the R3 times IB. And then over here, the first part we run into is the positive of the 21. So that's where we put the positive 21 there. If it was flipped, this would just become negative. and then we would just solve it the exact same way. Okay, any other questions about mesh? Do what? You should be able to do all quizzes now. Okay? So one thing I wanted to talk about, which was kind of fun, is kind of an application of logs. Okay? So stick with me. It's kind of more of a story time than anything. The idea is, so keeping some of this material in mind. I just looked this stuff up, so this is current as of yesterday. Okay? The largest hard drive that I could find is 16 terabytes. They sell commercially. I went to Newegg. This was the biggest one that I could find on their first page. I'm like, if I have to dig through 2 pages, it's not going to be there. So whatever they came up on their first page of items. So a 16 terabyte hard drive will run you about $470. This is actually better. Last year when I did this, these guys were $1,600. So 1 year, the price has gone down by a quarter, or to a quarter of the original price. That's the cool thing about this. So we're also going to be talking about Moore's Law. So Moore's Law, as I talked to you guys yesterday, is every between 2 years and a year and a half, the physical space, the dimensions of memory gets cut in half, and the physical capacity doubles. So that's one way to look at it. For the same size package, we can get twice the memory. For half the size, we can get the same memory. So basically what this is going to go is they're saying and it fluctuates between a year and a half and 2 years. We're going to use a year and a half just kind of as our baseline for this. So also when I was looking, because the nerd I am, I wanted to see how big of values as far as engineering notation do we have that are listed. So we have a terabyte, which is 10 to the 12th. We have a petabyte, which is 10 to the 15th. We have an exabyte, which is 10 to the 18th. An exabyte. So we got tera, peta, exa, and this is just what we've named so far. There's bigger numbers than this. This is just what we've named and what we use.
Wait, when is somebody using exabytes?
Not necessarily exabytes, but just exa in general. Yeah, counting stars, counting grains of sand, that kind of stuff. A zettabyte, however you want to say it. And then the one that really interests me it's a yottabyte. That's why it interests me. I figured this out right after I watched The Mandalorian. Okay? We have a yottabyte. And I'm going to pronounce those T's with a soft T, with a Yoda. Okay? So here's my question. How long is it going to take us before I can own a yottabyte? I want to own a Yoda. Okay, that's what it comes down to. I want to own a Yoda. The original Yoda is a puppet, yes. But I want this Yoda. Yeah. It's going to be a lot. Okay. So with Moore's Law, so remember, every year and a half, it's going to double. So the equation we're looking at is 2 to the x, because this is for how things double. This is getting into binary as well. We go from 1 to 2 to 4 to 8 to 16 to 32, 128, all the way up the scale. So when we finally get up to 1 times 10 to the 24th bytes, this is what I'm after. So a 1 with 24 zeros. How do I solve for this value? You use logs. So this is the application of why we're learning it, because we want to solve to get to a iota byte. So we take the log of both sides. So log of base 2 times 1 iota is equal to the x number of periods that we have to have happen to get to that point. Okay? Every year and a half. So basically what we're looking at is every power that we raise here is going to be 1.5 years. So now, how do I solve for this guy? Because now I have log base 2 times, so we have base 2, our exponent, our argument. We convert it. Will our calculators do log 2? No. So we have log of 1 iota, remember, which is times 10 to the 24th, divided by log 2 No. So how many periods of doubling do we have to have? 79.726. So essentially 80 periods to get us to where we're well within this commercially owned iota drive. Military might have them, private industry might have them that they've created. One thing I know, Google has their main hub has 2 petabytes of data stored within it. Like I said, this was all stuff I was looking up yesterday. So it's going to take us 80 periods to get there. If each period's a year and a half, how many years before I can get a iota drive? 120 years. So outside of my lifetime. Huh? 121. I didn't do it before that. Last spring was my first semester. Okay, so roughly 120 years before I can get my iota drive. However, I want to say I have a iota drive in my computer right now. So I want it now. Think of the girl from Charlie and the Chocolate Factory. The hell is her name? Veruca Salt. I figured somebody would remember it. So figure Veruca Salt. I want it now. Okay? How many drives, how many 16 terabyte hard drives do I have to buy to give me a iota of space? Okay. Okay. So this was my original equation. I'm doubling every period. Okay. Gives me, and I'm trying to get to a total of 1 iota. Yes. So we convert this so we can get the exponent by itself. So we have log of base 2 times our argument equals our exponent. Does that make sense how we got the conversion? Okay. Our calculators cannot do log base 2. They can't. So the way we have to do it is we take the log of our argument divided by the log base 10 of the new base. Because log 10 by itself is 1. Yep. So for this conversion to work, because our calculators cannot do this function right here. Cannot do it. So this is what we have to do. Log base 10 of the argument divided by log base 10 of the base. That's how we have to put it into our calculator to get it to solve for it. 1 iota, which is times 10 to the 24th.
How much did that 16 terabyte drive cost?
$470. I got all that information here too. Trust me, I was having fun with this. Does that make sense though, Zach? The idea is we're trying to use logs to solve for something, actually make them worthwhile. So by taking log base 10 of 1 iota, so times 10 to the 24th. Divide that value by log base 10 to the 2, so we plug that into our calculator just like that. The answer it gives us is 79, which means our exponent is 79.726. So if we raise 2 by 79.726 times, it would give us 1 iota. So that's what we're looking for, is the number of periods. How many times do we have to take 2 and multiply by itself to get there? How many doubles do we have to have happen? If it was a triple, it would be 3 to the x type of thing. So we end up with 120. So now what we're looking at is how much, if I wanted to buy it now, how much would this sucker cost? So we take 1 yottabyte, divide it by 16 terabytes. Remember, we have 1 times 10 to the 24th divided by 16 times 10 to the, what's tera? 12? Just real quick, by using our power math, we can just take 24 and subtract the 12. We end up with that exponent, and we're left with 1/16. So this comes out to be 62.5 times 10 to the 12th number of drives I have to buy. This number comes out to be 62.5 trillion drives. Just to put it in perspective as far as terms of just regular numbers outside of the tera, giga, that kind of stuff. Yes. So 62 trillion drives. And how much money does it come out to be? You take this number, multiply it by 470. Quadrillion. Like I said, this is an absolute insane amount of money. $29.3 quadrillion to give me a Yoda drive. Or I just wait 120 years and buy one off the shelf for $470. Yes.
You want it now.
But I want it now. It's true. Yeah, so wait till next year. The price is going to drop by 4, so that's going to take it down to, I don't know, $9 quadrillion. And you figure the national debt is what, 300 trillion? So an eighth of the national debt is how much it would cost to get this many drives. I don't even think the freezer would help. I think you would overpower the freezer very fast. You couldn't find terabytes. Honestly, if we're to the point where we have yottabytes, yeah, the cheapest you're probably going to see is zettabytes, maybe. Because think about what we have now. A 16 terabyte hard drive we can buy, but what size of flash drives do you find? 4s, 1s, So even then, we're going to be seeing, 256 zettabytes. Or those are going to be what you find at the dollar store. A trillion. So meg. I think I got those wrong. Anyway, so a meg is 6, yeah. So a meg, oh, that's what it is. We skipped one. There we go. So a meg is million. A gig is billion. Tera is trillion. And peta is quadrillion. That's why I wrote this all down, so I wouldn't forget. Like I said, it's kind of fun, but it's just a fun little exercise to look at. We could solve whatever we wanted. All my question was how long is it going to take for this to happen? And we can gain all the knowledge from these. Okay. Here's another part of this example, another part of just how much information this is, okay? The human genome. If we were to take the human genome, which is your DNA strand of a single human person, you have 3.089 billion base pairs, okay? if you were to use one base pair as a byte of data, because it's either one set or a not, you'd have to have 3.89 billion bytes of data. Okay? Just to store the human genome. We're not even talking Jurassic Park level here. Those guys, like, in the movie, the books, or whatever, they were 2 or 3 orders higher of base pairs than what we had. So, with the genome, if you figure this, so we have 3.089 times 10 to the 6th base pairs. How many base pairs could fit in one of these 16 terabyte hard drives? Oh, that's also this one is also a SATA drive, not an SSD. SATAs are about 4 times the price, or SSDs are about 4 times this price. The difference between the two. So solid state doesn't take moving parts. It's all transistor and electronic controlled. Hard drives has a disk, and then it has the hand that rotates across it. So yeah, solid state drives are fast. Okay. Yep. Yeah. Not quite that much. I think you missed a power in there. But basically, what it ends up being is storing the 3 billion base pairs on a hard drive. You could store 5,180 people's information on one hard drive. Okay. That's yes. So the population of Chubbuck, we could store most of the people's genetic code on 1 terabyte hard drive. Okay. To put this in perspective, just because, like I said, I was having fun. There is 7.594 billion people on Earth, according to Google, as of yesterday. So that would require 1,500 drives to store every single person's genetic code that is on the Earth right now. That's it. Yeah, we're getting there. No. So just, kind of put that in perspective. So 1,500 drives to store everybody in the world. The U.S. has 328 million people. That would require 64 drives to store everybody. Okay. Now we enter the Matrix. Okay. How many of you guys have seen this movie? Okay. So the idea is there's an alien race that comes in. They enslave the human population for their energy. Because our bodies create a tremendous amount of energy. So they have it so you're literally in a stasis pod. You're alive, more or less. And you have this big jack that goes into the back of your head that is draining the energy in your brain as you use it. So instead of those electrical signals being sent to your body, like to actually move, your brain sends the command. The alien probe intercepts those commands so you don't move, and then that energy gets sent to their distribution network. So that's kind of the idea, is you have everybody living in this alternate reality that they're actually doing things, thinking things, whatever, and that energy is just getting transferred out and used by the aliens. With that, this took a little bit of research to find. I don't know how completely credible these values are, but these were the only ones I could find. I was curious because the other day we were talking about how much information the brain can store. Because this is just your physical characteristics. This is so we could clone your body. This is not your mind. This is talking just a physical clone. One study that they had, so the study came out to be that so in your brain you have synapses and you have neurons. The synapses are the actual storage. The neurons is what connects the synapses together and creates the thoughts, memories, that kind of stuff. Their guesstimate, and I say guesstimate because that's really what it is, was a human brain can hold 2.5 petabytes of information. Now think of that earlier with Google. Their entire website repository is 2 petabytes. So one human brain can still hold more information than the entire internet.
Incredible source.
Okay?
So if we can get computers up to the point of petabytes, we could technically make an AI efficient enough to be human
Yes. Yes. So again, that therein lies the scary thing. So like I said, we are 120 years away from yottabytes. Petabytes is the next step, like from where we're at right now with terabytes. So we're looking probably 40, 50 years if Moore's Law continues and we're still able to continue this climb for storage, where we could cross into the threshold where you could have a hard drive big enough to store everything that a human brain knows as we know it right now. That could change. Like I said, that's all subject to change. And out of the different studies I was reading, this was the only one that gave me a definitive volume for it. So it's one source. So far, let's see, Moore was, so when computers were first coming out, the early 40s, 50s, 60s, that time frame, I'm not sure exactly when it was. There has been several guys that have come out now and says Moore's Law is over. We can't continue Moore's Law anymore. We physically can't. Because, and partially he's right, because now we've gotten to the point where we are creating semiconductors, chips, that are almost on the atomic scale. We're almost down to the size of protons, neutrons, and electrons. Yeah, this is where we have to have the next big breakthrough. As soon as we break into quantum computing, crystalline storage, all this kind of stuff that we've been trying for, this is going to unlock the door for this stuff. Once we overcome that barrier, and you guys might be part of that. You could be working for a company that is working to break into the quantum computing mechanics. You're trying to get into the whole new world of physics just coming out of this class. There's a very real possibility you could be involved in this. Because you guys would be the ones helping set up and test and calibrate and verify the results for the researchers and scientists doing this kind of stuff. That's one of the things that your job entails for JT4, or so I've been told, is you are actually building stuff to catalog and match and see if you can detect new stealth planes, new stealth technologies, new energy signatures. That's part of what Area 51 is. It's a military lab. Okay? So, like I said, this was kind of fun, but as you get into it, it's like we're right on the cusp of this crossover to where we get into the petabytes. I have no doubt that petabytes is actually going to change and is going to get more and more. Because depending on who you studied, they may have difference. And the thing it came down to was they said they had about 4.5 bytes of information per synapse, and you had like 125 trillion synapses in your brain. How they actually went and counted every single one of those is beyond me, but that was their basis for their logic. As soon as we do that, like you're saying, AIs are going to become so much more influential, so much more useful. Because now you can have computers running around like robots. Robots running around like humans, sorry. They are computers. But the idea behind this is, like, we are right here on this cusp to get into this AI. And you guys are in the perfect situation to be able to jump in on this research. It's fun and it's exciting. I know I get excited and carried away with this kind of stuff, but really, that's kind of the heart and soul of electronics. Is we're breaking everything down because we're moving really hard into a digital world, quantum world, where everything can be quantified as a 1 or a 0. And we have to be able to understand how to manipulate those. How can we understand where those values come from? It's kind of scary at the same time, too, with how close we are to this cusp. Mm-hmm. And honestly, what we're talking about and thinking about now is the same stuff people were thinking about and talking about when this program got started 60 years ago. Because when this program started, it was one of the first in the country that was write off producing text to go into NASA. That was going into Boeing, to go into all these places that were building the space shuttles, that were building the Apollo missions, that were working on the communication systems to be able to communicate with something as far away as the moon. That was their next jump, was these communications and these technologies that existed. And now we've crossed that threshold. Now we're to this part where we're getting into quantum mechanics. If we were to come up and show somebody even a terabyte hard drive, they would just be blown. Okay, I'm trying to figure out where that was. I saw this come up on Facebook on one of my nerdy friends. They had posted this picture of what 256 meg hard drive looked like. It was in the crate, the size of a Volkswagen bus, that they were pushing up the loading dock. 256 meg. And now, I mean, even in your cell phones, I've got a little chip in here the size of a dime that's 32 gigs of space. Yeah. But that's become the new world. Yeah. Yeah. And this is what's cool. That's the cool part of electronics, is to see how this is going to evolve. Because this really is the future. Whether or not we actually get to the point where we're storing people's DNA codes on here, storing their brain patterns. Because honestly, to me, your physical makeup, just your biology, your DNA, is only half the equation. You have to have the rest of your mind. Because you can make a carbon copy of somebody's genetic blueprint, but they're not going to be the same person. They're going to have different memories, different things, situations going to occur. Their memories are going to be different, and how they act is going to be different. Anyway, I could go on and on, but I just wanted to show this to you guys as a practical, quote unquote, practical application of logs and of where this technology is going. So, with that, let's go ahead and go to break.